Recording. So there we go. Okay. So we're going to go through part C. Okay. So in part B, you extended the investigation if you had a quadratic factor and you looked at the relationship between quadratic factors, in terms of factors in general, part A and part B. So part A was all linear factors, and you should have found a relationship between the number of roots, the number of turning points, and number of inflection points. Now, I've seen some pretty good, from the work I've seen so far, I've seen some good conjectures. The correct conjecture for linear factors only is if you have, for example, a quartic, you have 4 factors, 3 turning points, and 2 inflection points. We actually can look at some of these graphs, not that one, it's not the same one, this one, and you can see that. So you've got 1, 2, 3 turning points, 1, 2 inflection points. Now, does that relationship hold true for the other ones? Well, that's a question that we're going to be going into by the end of this assignment. So in that one, we've got a quadratic. Okay, if I was to, for example, make my actually, no, that is a quadratic factor. What am I looking at? Yes, but in this case, we've still got 3. So we have a quartic here. Actually, that's not quartic, that's almost 5. What have I done? All right, never mind. Okay, so, well, in any case, you have order 5 polynomial. In this case, we actually have 1, 2, 3. It's an order 5. You can tell that because it's going up and then down here. It's not going up and up or down and down. So we have polynomial degree 5. We only have 3 turning points, but we have 1, 2, 3 inflection points actually. You can see the any part where it's starting to straighten out. So you'll find you have to write a different follow-up and find a different conjecture. But we're actually looking at part C. Okay. Several other possible combination factors of quartic polynomial. All right, I'm going to go back to looking at this image here, which I'll blow up for everyone here. Okay, and I'll just remind you of that. Now, what I drew here was essentially 8 different ways that a order 4 polynomial, a quartic, ladies. Thank you. All right, an order 4 polynomial can behave around the x-axis. I'll make an example now. Some of these will actually have an accurate shape. The only thing you could possibly change is essentially maybe the turning points might be higher or lower. But in this case, all the order 4 with 4 linear factors will look like this or upside down. So down and down instead of up and up as far as the arrows. However, other ones may not look like it. Assembly 2, very similar. When we go back to our assignment sheet for part C, we're looking at including polynomials having a real quadratic factor with complex conjugate roots. What does that mean? I'm not going to dwell on complex conjugate. We're going to do the assignment without even doing that. What do I mean by that is, going back to my image, you need to be looking for part C at polynomials that take either the examples from number 4 or number 5 or number 8. No, sorry. All right, the ones with delta 0, that is, yes, sorry, 4 and 5. Okay. That was another one. Oh yeah, sorry, 6. I just haven't wrote the delta there. Okay, I'll explain the difference. Let's go. Okay, so in the case of number 4, you have a quadratic factor that does have, in fact, it's a squared factor. So it touches at that point of alpha. All right, but this part is what we call irreducible. That's the one where discriminant was less than 0. So you couldn't find any real roots. You see what it does here. It had touches, but this part, it like bends over. It doesn't come back down to the axis. It just goes up afterwards. It doesn't have to look like that, though. It could go down, and the shape could be different. It could try, it could actually bend down, but not quite reach, and then go back up. It can actually do something else as well. So whereas this is an example of the shape of quadratics that look like this. If you want to pick number 4 to look at, I would suggest you pick one of 4, 5, or 6. Not all of them because it's too complicated, and I'll show you why later on. Question example 5 is the hardest one. That's if you have 2 quadratic factors and they have none of them have real roots. So both of them are examples of, so bx squared plus cx plus d. Discriminant 1 is less than 0. Ex squared plus dx plus f. Discriminant 2 is less than 0. You notice here, I've got that W shape, but it never gets below the x-axis. It doesn't have to be a W shape, but what it is, it's either entirely above or entirely below the x-axis if A is negative. Okay, it could be all sorts of different shapes, and I'll show you how later on. All right, now this one here is if it has 2 distinct linear factors. And irreducible quadratics. So in this case, it cuts twice, but then over here, it doesn't do anything with the x-axis. But the shape doesn't have to look like question 6. If you investigate this, you'll see that yourself. All right, so you have to kind of pick one of those. I suggest you just decide, all right, I'll do number 4 or do number 6. Number 5 is quite challenging. Okay, so I went to play around with this. I was actually kind of curious and seeing what is actually the different shapes you could possibly have. So I've made a little decimal thing. The first little part of this, just all it is graphing, is it has, if you look here, it's the order 4 polynomial, and I've just put the coefficients of each term. Why does that disappear? Oh, there we go. Okay, the coefficients of each term are now sliders. So I've decided, okay, so you can actually play around with this. I'm going to keep that one, the first one consistent. So there, if I play on this one, you can see what happens. It does to the shape. All right, and you can see here, you can change that one and you can move that one. Now, in all those changes, this will have an irreducible quadratic factor because, let's have a look. How many x-intercepts does that have? 2, yes. But it's an order 4 polynomial. So this is, everything I've done here would be an example of number 6. Basically, it doesn't look like number 6. Number 6 has 2 there, and it has something over here. Basically, there's an, yeah. But if you play around these sliders a bit more, you can actually make it, particularly if you play with the last one, you can get, okay, so now it's got 4 distinct real linear factors, but it's the same shape. I can move that shape up and down. See, there's actually plenty you can do. So you will probably discover by end of this investigation that there are certain limits to how many, in terms of your order of your polynomial, how many roots you can have, x-intercepts, how many stationary points and inflections. You've already noticed that you can have them, if you have an order 4 polynomial, you can have no more than 4 x-intercepts. You'll probably discover you can have no more than 3 stationary points and no more than 2 inflection points. However, could you go less than that? Let's have a look. Now, don't worry about how I've gone and done this because it's got more to do with, okay, this is actually an example of a quartic. Now, you can see here, we have no x-intercepts. How many stationary points do we have? Okay, so how many times would the tangent go flatten out? Once, just here. Now, if you imagine our little ruler line kind of flips it around, can you find any inflection points in this one? So if I was to swing that around, I haven't actually set up, unfortunately, haven't set up my little swingy thing on this thing, but you can imagine you've got a ruler, it's swinging around. There's actually no inflection points. It's actually possible to make a order 4 polynomial with 0 inflection points. I've just done it here. Okay. So, but you can play around. I'm just going to play around with this one. Okay. What can I do? Does that have any effect? No, it doesn't. Apparently it doesn't. Interesting. Oh no, sorry. That's actually this one. That's why. Okay, that actually has an effect. Okay. See now. See, it's still got no real roots, but you can actually, you've got 1, 2 inflection points, and you actually have 1, 2, 3 station points. That's interesting. So when you start playing around with with polynomials, you might find, you could probably find in your group of polynomials that you can have various different numbers of stationary points and inflection points for the ones that have no an irreducible quadratic factor. Now I'm just going to change my little thing over here. I'm going to look at another function that I've set up. Okay. All right. Here's another one. So this one has to do with, okay, what if I was to have this is another type of one. Now, this has essentially one inflection point, sorry. Technically it is counted as inflection point, but not the way that we discussed it. It's the way that it would actually count as one in stage 2. Ladies, thank you. All right. Now I've got a little slider here that's actually going to affect the vertical displacement of this. So if I set up like this, it has no roots. But if I put up here, it has 2 roots and 1 irreducible quadratic factor. Either way, it has only 1 stationary point. That's another example. So you can find for yourself as you go through this, and you examine different types of quadratics. Thank you. All right. So one way you can do this is by setting up your own quadratic. So if, for example, you said, okay, I want to do ones that look like number 4. Okay. Well, I might set up something like that. Let's just see how you could go and do that. Well, you can just go play around with some sliders and come up with your own. That's probably the quickest way to do it. So I'm going to come up with a new function. Okay. I'm going to say, I don't think I've used a simple Q, so let's do Q1. Q2 squared. And then I want to have, you've got to be careful with this one. You've got to make sure that whatever your numbers are for the rest of these, they end up, I'm just going to do x squared minus Q3 x. Let's do plus. What am I doing? Plus Q4. Okay. So let's put up sliders for all of those. I just have to make sure that for the quadratic factor, yes, like this one here. So I'm just going to say put those at the default. It's what's important is that the values here, the discriminant would be equal to a negative number. Now, if you do that, okay, now essentially here, my A is 1, my B is 1, and my C is 1. Well, let's go calculate that. All right, if I just put it in my calculator. Okay, so remember, discriminant is B squared minus 4AC. So if I do 1 squared, which is 1 minus 4 times 1 times 1 is negative 3. So just when you play around with this, check that this is still has no real roots. That's all you got to do. And then you can play around with these. So if I was to say change this one up, like basically you know when it's not, if you do the graph, because now, well, let's check it. Well, I've got it at, let's do it at, if I do -1. Okay, well, you know that you've done something wrong because you've got more x-intercepts. But check it again. So if I do my calculator, so I've changed C into -1. So 1, 1, and -1. Well, what if I did that? 1 B squared, sorry, 1 squared minus 4, oops, B squared minus 4 times A. One more time. B squared, 1 squared is 1, minus 4. Ladies, what's on? 4, you're ruining my recording. Okay. Times A, should be using scientific calculators. Anyway, basically what the idea is ends up being minus 1 minus 4 times 1 times minus 1 is 1 plus 4 is positive 5. So I won't do it on the calculator, should use the scientific for that. But how can I fix that? Well, maybe if I made my, change my A, I could make my A larger, that would change it. So eventually you'd end up with, or change it the other way. You can play around these factors, just make sure you check the numbers of that and make sure that your discriminant is negative, and it can be used as an example of complex conjugate having a real quadratic factor, a real quadratic factor. You can pick 5 and do both. That's probably the most challenging one because there is so many different variations to that. Like there's so many, basically you can think of any way you can draw a order 4 polynomial. If it ends up entirely above the x-axis or entirely below, if it's upside down, and the a is -1, then it will be an example of this. Okay, so go through, do as many examples, like pick one of these, do lots of examples of this, see how, have a look for what is the minimum number of stationary points you can find, what is the minimum number of inflection points you can find. And part C is your kind of, this is the one that gets you the higher grade. If you thoroughly go through part C, that's what will give you a really good mark for this assignment, because particularly part A, you've been instructed how to go about doing this, more or less for part B. But part C, you have a lot more freedom for things to pick. Hopefully, what I've recorded here now will help you investigate that in further detail. Okay, I'm going to end this recording. So let's have a look here. All right. Stop recording.